service disconnect is necessary to isolate the electrical system from the power source. This isolation is crucial for safety during maintenance procedures or in the event of an emergency. The primary purpose of a service disconnect is to allow for the complete de-energization of the electrical system, preventing the risk of electrical shock or other hazards when work needs to be performed. The service disconnect should be located before the meter. This placement is as close as possible to the point where the electrical service enters the building. The reason for this proximity is to ensure that the entire electrical system within the building can be de-energized quickly and efficiently. Placing the disconnect at the entry point minimizes the amount of energized wiring that remains when the disconnect is opened. Grounding is essential for electrical safety. The electrical system must be properly grounded. Grounding provides a low impedance path for fault current. This path allows protective devices such as circuit breakers or fuses to quickly interrupt the circuit in the event of a ground fault. Without proper grounding, fault currents could flow through unintended paths, such as a person touching a faulty appliance, leading to electrical shock. Grounding also protects against electrical shocks. By providing a low impedance path to grounding helps to ensure that the voltage potential between conductive surfaces and the earth is minimized. This minimizes the risk of electrical shock if a person comes into contact with a live conductor. Grounding also prevents overvoltages. Overvoltages can occur due to lightning strikes, utility switching, or other transient events. A properly grounded system provides a path for these overvoltages to dissipate safely to ground, protecting equipment and preventing damage. Grounding should be done in accordance with the National Electrical Code, also known as NEC, and any applicable local codes. These codes provide detailed requirements for grounding electrical systems, ensuring that they are installed safely and effectively. The installation typically involves installing a grounding electrode. A grounding electrode is a conductive object that is buried in the earth and connected to the electrical system. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. A ground rod is a metal rod, typically made of copper or copper-clad steel, that is driven into the ground. The NEC specifies the minimum length and diameter of ground rods as well as the depth to which they must be driven. A ground plate is a metal plate that is buried in the ground. Ground plates provide a larger surface area than ground rods, which can be beneficial in areas with poor soil conductivity. Metal water pipes can be used as grounding electrodes if they meet certain requirements. The water pipe must be in direct contact with the earth for at least 10 feet, and it must be electrically continuous. The grounding electrode is connected to the electrical system. The connection is made using a grounding electrode conductor. The grounding electrode conductor is a wire that connects the grounding electrode to the electrical system's grounding busbar or terminal. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The grounding busbar or terminal is a conductive bar or terminal that serves as the central point for grounding connections in the electrical system. All grounding conductors in the system are connected to the grounding busbar or terminal. In addition to the grounding electrode, the NEC also requires the use of a bonding system. The bonding system connects all metal parts of the electrical system together, ensuring that they are at the same electrical potential. This helps to prevent electrical shock by minimizing the voltage difference between conductive surfaces. Bonding conductors are used to connect metal enclosures, conduit, and other metal parts of the electrical system to the grounding busbar or terminal. The size of the bonding conductors is determined by the size of the circuit conductors. The NEC also requires the use of ground fault circuit interrupters, also known as GFCIs, in certain locations. GFCIs are designed to protect against electrical shock by detecting small ground faults and quickly interrupting the circuit. GFCIs are typically required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. In summary, a service disconnect is required to isolate the electrical system. It should be located before the meter, and proper grounding is essential for safety. Grounding should be done in accordance with the NEC and local codes, involving a grounding electrode connected to the electrical system, along with a bonding system and GFCIs for enhanced protection. The National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations, including specific requirements for service disconnects and grounding systems. These requirements are designed to ensure the safety of people and property by minimizing the risk of electrical shock, fire, and other hazards. The NEC is updated every 3 years to reflect the latest advances in electrical technology and safety practices. The NEC specifies the requirements for the size and type of service entrance conductors, the overcurrent protection devices, and the grounding system. It also provides detailed instructions for installing and maintaining electrical equipment. The NEC is adopted by many states and local jurisdictions, and it is used as a basis for electrical inspections. Electrical inspectors ensure that electrical installations comply with the NEC and other applicable codes. Compliance with the NEC is essential for ensuring the safety and reliability of electrical systems. Failure to comply with the NEC can result in fines, penalties, and even legal liability. The NEC also addresses the specific requirements for service disconnects. A service disconnect is a device that is used to isolate the electrical service from the building's electrical system. This allows the electrical system to be safely energized for maintenance or repairs. The NEC requires that a service disconnect be readily accessible and located at a convenient point near the entrance of the service conductors. The service disconnect must be capable of interrupting the maximum available fault current at the service entrance. The NEC also specifies the requirements for the type and size of the service disconnect. The type of service disconnect that is required depends on the size of the electrical service. For small services, a simple disconnect switch may be sufficient. For larger services, a circuit breaker or fuse disconnect switch may be required. The size of the service disconnect must be large enough to handle the maximum current that is expected to flow through the service conductors. The NEC also addresses the specific requirements for grounding systems. A grounding system is a system of conductors and electrodes that is used to connect the electrical system to the earth. This provides a path for fault current to flow back to the source, which helps to protect against electrical shock. The NEC requires that all electrical systems be properly grounded. The grounding system must be installed in accordance with the NEC requirements. The NEC specifies the requirements for the type and size of grounding electrodes, the grounding electrode conductor, and the bonding conductors. The type of grounding electrode that is required depends on the soil conditions and the size of the electrical service. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. The grounding electrode conductor is the conductor that connects the grounding electrode to the electrical system. The size of the grounding electrode conductor must be large enough to handle the maximum fault current that is expected to flow through the grounding system. Bonding conductors are used to connect metal parts of the electrical system together. This helps to ensure that all metal parts are at the same electrical potential, which reduces the risk of electrical shock. The size of the bonding conductors must be large enough to handle the maximum fault current that is expected to flow through the bonding system. In addition to the NEC requirements, local codes may also have specific requirements for service disconnects and grounding systems. It is important to check with the local authorities to determine the specific requirements that apply in your area. Proper grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, which helps to protect against electrical shock. Bonding connects metal parts of the electrical system together, which helps to ensure that all metal parts are at the same electrical potential. Ground fault circuit interrupters, or GFCIs, are another important safety device that can help to protect against electrical shock. GFCIs are designed to detect small ground faults and quickly interrupt the circuit. GFCIs are typically required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. Electrical safety is everyone's responsibility. By following the NEC requirements and taking other safety precautions, you can help to protect yourself and others from electrical hazards. If you are not comfortable working with electricity, it is always best to hire a qualified electrician. Electrical work can be dangerous, and it is important to make sure that it is done correctly. Here's a more detailed breakdown of grounding and bonding concepts. Grounding refers to connecting the electrical system to the earth. This connection provides a low impedance path for fault current to flow back to the source. The grounding electrode is the physical connection to the earth. It can be a ground rod, a ground plate, or a metal water pipe. The grounding electrode conductor connects the grounding electrode to the electrical system's grounding busbar or terminal. The size of this conductor is determined by the size of the service entrance conductors, as per the NEC table 250.66. Bonding, on the other hand, involves connecting all metal parts of the electrical system together. This includes metal enclosures, conduit, and equipment grounding conductors. The purpose of bonding is to ensure that all metal parts are at the same electrical potential. This minimizes the risk of electrical shock if someone comes into contact with a live conductor and a metal part of the system. The equipment grounding conductor, or EG, is a crucial part of the bonding system. It provides a low impedance path for fault current to flow back to the source from metal enclosures and equipment. The size of the EGC is determined by the size of the circuit conductors, as per NEC table 250.122. The main bonding jumper, or MBJ, is the connection between the grounded conductor and the equipment grounding conductor at the service equipment. This connection is essential for establishing a solid grounding path for fault current. Ground fault circuit interrupters, or GFCIs, are designed to protect against electrical shock by detecting small ground faults. A ground fault occurs when current flows through an unintended path, such as a person's body. GFCIs are required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. Arc fault circuit interrupters, or RFCIs, are designed to protect against fires caused by arc faults. An arc fault is an unintentional electrical discharge that can generate heat and ignite nearby materials. RFCIs are typically required in bedrooms and other areas where there is a high risk of fire. The NEC provides specific requirements for the installation of service disconnects and grounding systems. These requirements are designed to ensure the safety of people and property. It is important to follow the NEC guidelines when installing electrical systems. Here are some additional details about specific NEC sections relevant to service disconnects and grounding. NEC Section 230 covers service entrances. This section provides requirements for the service conductors, overcurrent protection, and service disconnects. NEC Section 250 covers grounding and bonding. This section provides comprehensive requirements for grounding and bonding electrical systems. NEC Section 300 covers wiring methods. This section provides requirements for the installation of wiring and cables. NEC Section 310 covers conductors for general wiring. This section provides requirements for the size and ampacity of conductors. NEC Table 250.66 is used to determine the size of the grounding electrode conductor. NEC Table 250.122 is used to determine the size of the equipment grounding conductor. Understanding the concepts of grounding and bonding and following the NEC guidelines is essential for ensuring electrical safety. Always consult with a qualified electrician if you have any questions or concerns about electrical installations. Furthermore, let's clarify some common misconceptions about grounding and bonding. One common misconception is that grounding protects against electrical shock. While grounding does help to reduce the risk of electrical shock, it is not a foolproof protection. The primary purpose of grounding is to provide a low impedance path for fault current to flow back to the source. This allows protective devices, such as circuit breakers and fuses, to quickly interrupt the circuit in the event of a ground fault. Another misconception is that bonding is only necessary for metal parts of the electrical system. Bonding is also necessary for non-metallic parts of the system that could become energized, such as plastic conduit. Bonding ensures that all conductive parts of the system are at the same electrical potential, which minimizes the risk of electrical shock. It's also important to note the difference between a grounded conductor, also known as the neutral, and an equipment grounding conductor. The grounded conductor carries current under normal conditions, while the equipment grounding conductor only carries current during a fault. The grounded conductor is intentionally connected to ground at the service equipment, while the equipment grounding conductor is connected to ground at the equipment. The separation of these conductors is crucial for preventing unwanted current flow in the equipment grounding conductor. Now let's discuss some practical considerations for installing grounding and bonding systems. When installing a ground rod, it should be driven into the ground at least 8 feet deep, as specified by NEC section 250.53. The top of the ground rod should be flush with or below the ground level. When using a metal water pipe as a grounding electrode, it must be in direct contact with the earth for at least 10 feet, and it must be electrically continuous. Any insulating fittings or coatings must be removed to ensure a good electrical connection. When bonding metal enclosures, bonding jumpers should be used to connect the enclosures together. The bonding jumpers should be sized according to NEC table 250.122. When installing GFCIs, they should be located in readily accessible locations. Test the GFCIs monthly to ensure that they are working properly. Electrical codes can vary slightly from one location to another. It is important to check with the local authorities to determine the specific requirements that apply in your area. Proper electrical safety practices are essential for protecting yourself and others from electrical hazards. Always follow the NEC guidelines and consult with a qualified electrician if you have any questions or concerns. Remember that electricity can be dangerous. Never attempt to work on electrical systems unless you are qualified and trained to do so. If you are not comfortable working with electricity, always hire a qualified electrician.